What is so wonderful about rainbows? Those are just a mixture of colors blended nicely, right? Now take the case of prism. We can see that when sunlight passes through the prism, it splits the sunlight into 7 colors. What could be the reason behind it? And we know that fingerprints are unique to each person. Its uses vary from unlocking a phone to solving crimes. Then, what about the identification of elements and unknown compounds? Is there any way to identify unknown samples? Starting with the mystery of rainbows, we will further expand into the idea of spectrum in general and different types of spectra, and finally, we will discuss the line spectra of hydrogen in detail. The rainbow, which we see on some humid days, are as a result of bending of white light. The beam of light is deviated or refracted from its original path as it passes from one medium to another. Now, let us have another look into the refraction of light in a prism. It is observed that when a ray of white light is passed through a prism, the wave with shorter wavelengths bends more than the one with longer wavelength. One thing to note here is that ordinary white light is composed of waves with all the wavelengths in the visible range. This series of colored band in a white light is called the spectrum. The light of red color, which has longest wavelength, is deviated the least, while the violet light, which has shortest wavelength, is deviated the most, as you can see here. The spectrum of white light, which you can see here, ranges from violet at 380 nanometer to red at 750 nanometer. Here you can see that violet merges into blue, blue into green, and so on. Due to this continuous nature of spectrum, such a spectrum is called continuous spectrum. This similar spectrum is the same one which we see in rainbows formed in sky. As you can see here, visible light is just a small portion of the electromagnetic radiation. When electromagnetic radiation interacts with matter, atoms and molecules may absorb energy and reach to a higher energy state. With higher energy, these are in an unstable state. For returning to their normal state, which are more stable and are of lower energy, the atoms and molecules emit radiations in various regions of electromagnetic spectrum. As we have observed now, spectrum of radiation emitted by a substance that has absorbed energy is called emission spectrum. The atoms, molecules or ions that have absorbed radiation are said to be in an excited state. In our last case, we have observed that when white light passes through a prism, it produces a continuous spectrum as shown in the first picture here. To produce an emission spectrum, energy is supplied to a sample by heating it with light. Here, for example, a gas is heated, and then the wavelength of the radiation emitted by this hot gas is recorded as the sample gives up absorbed energy. The resulting spectrum is known as emission spectrum, which will specifically show the lines corresponding to the radiations emitted by the sample. Compared to emission spectrum, absorption spectrum is like the photographic negative of an emission spectrum. So why it is called photographic negative? Here radiation is passed through a sample. Here, for example, a cold gas. This cold gas absorbs radiations of certain wavelengths and then it transmits the radiation through the prism. When you look at the spectrum, there will be some dark spaces in the continuous spectrum which corresponds to the missing wavelengths which has been absorbed by the cold gas. This type of spectrum is called absorption spectrum. This study of emission and absorption spectra is referred to as spectroscopy. This branch of chemistry deals with the interaction of electromagnetic radiation with matter. As you can see here, the absorption spectrum results from absorbing electromagnetic radiation and showing a spectrum with vacant dark spaces. The sample shows emission spectrum when the sample comes back to the ground state by emitting radiations. The resulting spectrum is measured in a device and the data is recorded as a plot showing the lines corresponding to the radiations. We have seen already that white light shows a continuous spectrum because all the wavelengths from red to violet of the visible light are represented in the spectra. The emission spectra, on the other hand, do not show a continuous spread of wavelengths from red to violet. Instead, they emit light only at specific wavelengths with dark spaces in between them. Such spectra are called the line spectra or atomic spectra because the emitted radiation is identified by the appearance of bright lines in the spectra. Now, let us see how the emission and absorption spectra of hydrogen atoms are obtained. Here, in the first case, light emitted by a sample of excited hydrogen atoms, or you can take any other element, can be passed through a prism and separated into certain discrete wavelengths, as you can see here. Thus, an emission spectrum, which is a photographic recording of the separated wavelengths, is called as line spectrum. If you look at the emission spectrum, you can see many lines. This is because there are many atoms of hydrogen and each of them can have many possible excited states. The light emitted as these atoms fall to their lower energy state is responsible for the spectrum. The second case is an example of absorption spectra of hydrogen. When white light is passed through unexcited atomic hydrogen and then through a slit and prism, the transmitted light is lacking in intensity at the same wavelengths as are emitted in the emission spectrum given above. The recorded absorption spectrum is also a line spectrum and the photographic negative of the emission spectrum, as you can see here. Line emission spectra is mainly used in the study of electronic structure. The important thing to note is that each element has a unique line emission spectrum. The characteristic lines in the atomic spectra can be used in chemical analysis to identify unknown atoms. This can be compared with the fingerprint analysis, where fingerprints are used to identify people. This is also used to find the unknown composition of materials. And spectral lines emitted by distant stars and nebulas are used to study the galaxies and universe in general. We will limit our discussion to the determination of electronic structure of samples. To identify an unknown sample, the lines in the emission spectra of an unknown sample is matched with the lines of emission spectra of the atoms of known element. This way, we can identify the unknown sample. German chemist Robert Bunsen was one of the first scientists to use the line spectra to identify elements. Elements like rubidium, cesium, thallium, indium, gallium and scandium were discovered when the minerals were analyzed by spectroscopic methods. The element helium was discovered in the sun, that too by using spectroscopic methods. Now that we have covered the basics of the line spectra, let us look into the line spectrum of hydrogen. When an electronic discharge is passed through the gaseous hydrogen, the hydrogen molecules dissociate and energetically excited hydrogen atoms produce and emit electromagnetic radiations of discrete frequencies. The Swiss scientist Johann Balmer showed in 1885, based on experimental observations, that if spectral lines are expressed in terms of wave number, that is nu bar, then the visible lines of hydrogen spectrum obey the following formula. Wave number nu bar is equal to 109677 into 1 by 2 square minus 1 by n square, where n is an integer equal to or greater than 3, that is n equal to 3, 4, 5, etc. The series of lines described by this formula are called Balmer series. The Balmer series of lines are the only lines in the hydrogen spectrum which appear in the visible region of the electromagnetic spectrum. Another Swedish spectrochemist named Johan Rydberg noted that all series of lines in the hydrogen spectrum could be described by another general formula. Wave number nu bar is equal to 109677 into 1 by n1 square minus 1 by n2 square, where n1 is equal to 1, 2, etc. and n2 is equal to n1 plus 1, n1 plus 2, etc. The value 109677 centimeter inverse is called Rydberg constant for hydrogen. After Balmer, many scientists found about different lines in the hydrogen spectrum. The first 5 series of lines that corresponds to n1 equal to 1, 2, 3, 4 and 5 are known as Lyman, Balmer, Paschen, Brackett and Fun series respectively. The transition for each of the series is as given in the table. That is, for Lyman series, the transition occurs from second line onwards, and these lines correspond to the ultraviolet region. For Balmer series, the transition occurs from the third line onwards to the second line and falls in the visible region as we have explained in the last slide. Paschen, Brackett and Fun series corresponds to the infrared region in the electromagnetic spectrum. Here transition occur to the third, fourth and fifth line respectively from the higher energy levels. This picture shows the transition of the electron in the hydrogen atom. As you can see, the transition occurs to n equal to 1 for Lyman series, n equal to 2 for Balmer series and n equal to 3 for Paschen series. Other transition series are from higher energy states, so it is difficult to show in this picture. Of all the elements, hydrogen has the simplest line spectra and the spectra become more complex as we consider heavier atoms. Some features which are common to all spectra is that it is unique for each element and there are some regularity in the spectra of each element. There are many questions that may arise based on what we discussed so far. The main question is, what are the reasons for these similarities in the spectra? Does it have something to do with electronic structure of atoms? These are the questions need to be answered. We shall find later that the answers to these questions provide the key in understanding the electronic structure of these elements. A scientist named Niels Bohr provided some valuable insights into these details by explaining the hydrogen spectrum. We will see more about this in our next class. With this, I will summarize this video.
Manorama Horizon. Learning made simple.